Today we're going to be looking at a nuclear reactor simulator. This one was done by University of Manchester. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. And this reactor design, just by looking at it, appears to be a 4-loop pressurized water reactor, the same one at the plant that I worked at. And over 5 of those 10 years were in the control room as a reactor operator and as a shift supervisor. So I should be pretty good at this game, right? Watch me fail horribly at this. All right, nickname. Just go with my channel's initials. They don't need to know this.
Welcome to the University of Manchester's Nuclear Reactor Simulator. This is a pressurised water reactor.
Love the accent on the virtual assistant here. Fun little background music. Let's take a tour.
It uses nuclear fission to heat water to make steam. The steam drives a turbine which powers a generator, and this makes electricity.
That's a pretty good explanation and simplification. I love them keeping it nice and high level. This is clearly intended for people to play with and get a little bit more knowledge with nuclear power, which I fully support.
In nuclear fission, a neutron hits a uranium-235 atom and is absorbed by its nucleus, which becomes unstable and splits into 2 smaller nuclei, giving out a burst of energy and 2 or 3 more neutrons. These neutrons hit other uranium nuclei, resulting in a chain reaction.
This process is extremely fast. They say it like, oh, it hits, becomes unstable. Yeah, we're talking fractions of a nanosecond. So it hits it, it essentially splits right away before you can even realize what happened, which is cool.
The nuclear fission reaction happens in the reactor core. This is where the uranium
I love
fuel
these analogies they use. Train wagons full. Yep. Just shows you how horribly inefficient coal is, at least compared to nuclear. But hey, coal served its purpose, getting us going through the Industrial Revolution, but now it's time for more fun stuff.
The control rods absorb neutrons to regulate the nuclear reaction, and in turn, the amount of heat produced in the reactor core.
This can fall in and stop within 4 seconds. The plant I worked at was less than 3. Chernobyl was on the order of 20, which is unacceptable. That's way too slow for you to be pumping the brakes with the control rods fully inserting. And they're showing on this icon that rods are temperature. And that rod's affecting temperature. You withdraw rods, the end result is reactor coolant temperature is going to go up. You're causing more fissions. It's going to which will stabilize at a higher reactor coolant temperature. Now, one thing to keep in mind, they're not showing units here for simplicity. The far left isn't 0, and the far right isn't the maximum temperature it can possibly withstand. The far left is probably on the order of 560 degrees Fahrenheit, and the far right is on the order of 630 degrees Fahrenheit. So it's a pretty short range. And considering the amount of water that's in there and the amount of temperature and pressure, 1 degree has a lot of impact on thermal expansion. Pressure is on the order of 2235 psi, by the way.
Coolant is water that is pumped to the reactor core to absorb the heat produced by the nuclear fission process.
So not only does it absorb the heat, but it transports the heat to the steam generators and ultimately converts it into usable energy in the form of electricity. So yes, it cools the reactor, but it's also the primary method of transport. What it also does is, like it says there, it slows down the neutrons. It says making the fission reaction more effective. Yes, you would not have a fission reaction during a loss of coolant accident. You lose the coolant, the reactor's shut down because nothing's slowing down those neutrons, meaning they're not going to fission. That is one thing you don't have to worry about, is shutting down the reactor when you lose the coolant. When you do, you activate your emergency core cooling system to keep the shutdown reactor cooled. And that's because of decay heat. The reactor will still generate heat after it's shut down. On the order of 1% and dropping logarithmically, but 1% is still a lot of over 3 gigawatts of heat for a typical pressurized water reactor.
The pressure vessel houses the reactor core.
And it is quite heavy. You need a super crane, and you need to take the lid off of the reactor containment building in some cases to lower it in, or you actually have to kind of break it up into smaller pieces. That's a crazy thing that is not done very often, but they took the top off for the new nuclear reactors that were under construction in Georgia.
The coolant pumps move the coolant around the reactor.
And I like this. It's showing like off or on. These pumps are typically single speed. So presumably when you hit that button, it should just go to 100% of normal. Could empty an Olympic-sized swimming pool in 80 seconds. Yep. One individual pump is on the order of 100 to 130,000 gallons per minute. And what's interesting is, so you start them up individually. You don't want to turn them all on at once because we're talking megawatts of pumps. These are really, really big. They're about 10, 12 meters tall. So you turn them on one at a time, and you turn one on, you're actually going to see backwards flow in the other 3 loops with just one reactor coolant pump running. It looks like for the purpose of this simulator, though, this is looking at all 4 loops, which is fine.
The coolant is kept under great pressure by the pressurizer to stop it from boiling, even when it reaches 325 degrees Celsius.
Yes, and here you're at a higher pressure, higher temperature, which helps for thermodynamic efficiency, because it's the difference in temperature between your hot reservoir and your cold reservoir. Another way to improve efficiency is just when it gets cold outside naturally, because water gets taken in from a large reservoir, and that water is taken in and just goes to the condenser. Now, we're talking about, when I say the condenser, we're outside of the nuclear part of the plant and into the same steam generation part of the plant that exists in coal plants, natural gas plants, anything with a thermal cycle. But that's where your efficiency comes from, is that temperature difference between the steam generator and...
The hot, pressurized coolant is pumped to the steam generators, where it heats a second circuit of water to turn it to steam.
Yeah, exactly what I was talking about. Yep, that's all that circuit does, and it exists in every other plant. So here we're looking at steam demand, and how you control this is the main turbine governor valves, and just affects how much steam is flowing to the turbine. And reactor power follows steam demand in a pressurized water reactor. So you increase steam flow by 5% of rated thermal power, reactor power is going to go up by 5%, and that's the end result. But you increase steam flow, reactor coolant temperature is going to drop, which is why you withdraw control rods to maintain temperature. It's interesting, when you're synced to the grid, the turbine is power, and the rods and the control rods are temperature. Now, physics isn't any different. Control rods still raise power, but from a control mechanism, you say that just because it's easier to control that way. Because that's the mindset you have as an operator when you are controlling power and temperature. You'll see what happens when we start the game, I'm assuming.
The steam leaves the steam generators and flows through the turbines, making them spin.
Yep. And interesting, it's exactly like a kettle. And it's actually the same phenomena that happens after you've been making a lot of... and you have a little bit of impurities that gather at the bottom. There is a loop Not going to be shown in this game because this game's designed to teach you about nuclear physics, not secondary plant cleanup. But there's a purification loop that sucks out the bottom of the steam generators to essentially clean the bottom of your tea kettles. It purifies it, keeps that water good and pure. And then you want it pure because steam generators, steam separators at the top can be highly sensitive. So you want that water nice and pure. And that actually also affects the quality of your steam, leading to a more efficient cycle.
The spinning turbines power a generator. They turn a magnet inside it to produce an alternating current. This electricity then leaves the generators to be supplied across the country.
I love these factoids. In 1 hour, this nuclear reactor can generate enough power to run a UK home for 400 years. Maybe by 400 years, we'll finally have fusion.
The steam that turned the turbines is condensed back into water by the condenser to flow back to the steam generators and then become steam once again.
Yep, and that completes the secondary loop. Does the sea, a lake, or a river? The plant I worked at, it was essentially a lake, a reservoir. Allegedly, you'd see gators at that reservoir. I've never seen one personally, but that could just be some operator's old night shift tale, though.
Step 1. Switch on the
nice.
coolant
Shows you how to
pumps.
play.
You can explore the reactor at any time by clicking on the 2D diagram. Step 2. Lift the control rods by about 10%. You can see the percentage they
This
are
is all
raised
very
by clicking
fast.
Control rods on the 2D diagram. Step 3.
But I can see how you do
Increase
that
the
just to
steam
learn.
output to start producing electricity. Try to match your output to the power demand.
Okay, this is something you would never do in real life. Nuclear plants have right-of-way. Certainly within the US, and I can't imagine the UK doing anything differently. And there's a reason for that. And the reason for that is xenon is produced, which effectively acts as another set of control rods. Now, it can build in and burn out over time. What you need to know for reactor operations is you like having xenon at an equilibrium concentration because that makes it easier to maintain reactor power at 100%, or if you're doing a hold for 50%, so on. I can tell this isn't modeled by the game. And it can be kind of a pain, because if you lower reactor power by, say, 50%, it's gonna peak, you're gonna have a peak of xenon hours later. A rule of thumb is it's the square root of your percent reduction. So you cut power by 50%, square root of 50 is about 7. So in 7 hours, you're gonna have a xenon peak that's gonna bring down power even further. So you're gonna need to either dilute the reactor coolant system, remove boron to essentially raise power, or withdraw control rods. And this is gonna raise temperature, to maintain power at that 50%, so xenon doesn't shut you down. And that's just a pain to work with. It's expensive because it involves using a lot of ultra-purified water to change reactor coolant concentration, and it just gets into a big mess. So nuclear power plants are not designed to be load-following plants. They're designed to be base load, where they get up to 100% power, and they stay there for 18 to 24 months at a time. But I guess for the purpose of the game, we're gonna vary power level by varying steam demand over the course of a day. That's very different, but we'll see if we can do it. All right, let's try this.
First, turn on the coolant pumps.
You're almost ready to start making electricity, but the coolant is heated up. So
Now, raise the control rods.
So we're on. So the reactor is on, but we're not actually making any power yet. Now that is a time that happens. But here, we'll go ahead and withdraw some control rods.
Warning: energy output too low.
Energy output too low. Oh, because we're not making demand. So we'll go ahead and. Okay, so coolant got a little bit high. That's interesting. I guess because we didn't have enough steam and
Warning: energy output too low.
This is funny. I have -5 points.
Warning, energy output too low.
You'd be slow in opening up this Steam. There we go. Apparently I wasn't holding down P enough. But yeah, this is one of those, it looks like just keeping your stuff in the green band kind of dealios.
Warning, energy output too low.
Doesn't go very fast. There we go. Yeah, pretty simplistic. Or now it's showing demand falling over the course of the day. Again, you never want to do this with a nuclear plant. It's fairly stable, fairly slow. What's interesting is reactor coolant flow actually stays about the same. I think they might be using it as an analogy for like overall steam flow and feed flow, because that's mainly what you look at when you look at steam demand. Reactor coolant flow stays about the same more or less. So I think they're looking at steam generator flow and feed water flow is what this is kind of acting synonymous for. So that's a bit weird. But I can see for the purpose of 3 parameters to pick for doing this. By the way, you'd have more than one operator doing this. Obviously, there's a lot more complicated systems at work here. And you typically have one operator would be adjusting control rods, or one on the turbine. Each one would have a peer checker and a supervisor providing oversight. Someone who has a senior reactor operator license, just like the one that I had, providing that. But for the purpose of a little educational tool, I can understand why they made it nice and simplistic like this. Just so you can kind of see what happens, and also just basic operational theory and just seeing how one system affects the other. Even though it's not... They're missing a few things, of course, but I think this is definitely cool in that it's, getting certain people involved. Whoa! Well done, you powered the nuclear reactor. Can you beat your score? Continue playing on another day. In one day, use 118 kilograms of fuel, and to run coal, you need 14 million kilograms of coal. That's another reason why coal power plants are significantly smaller than nuclear power plants, because it just doesn't produce nearly as much. All right, let's try day 2. So today we're gonna deliberately throw something out of band and see what happens.
Warning, energy output too high.
Yeah, let's overpower this thing. It should automatically shut down. Come on. Are you going to trip the reactor?
Warning, energy output too high.
Let's lower temperature so we'll get a... Okay, here we go. You can start playing again when the control panel lights back up.
Warning, energy output too low.
Oh, so it automatically restarted. That's not a thing. You wouldn't be able to catch it like that. You'd have to go through a detailed investigation to find out.
Warning, energy output too low.
Let me go ahead and turn the sound off. But yeah, so the reactor shut down to a safety measure. It doesn't specify what it is. What it would be a combination of overpowering the thing, and there's a rate trip called overpower delta temperature, and really what that means is you're producing way too much power for how much temperature you're at, which is why I started, in order to get it to hurry up the trip process, I lowered I inserted control rods to lower temperature, but at an extremely high power. So you get that much of a mismatch and it shuts you down. And there are other things to do that. I'm surprised I didn't exceed a rate parameter when I opened the steam generator. It was all the way up in terms of just straight up overpowering, but you can see the time is progressing rapidly, so there's a lot of time compression going on. And another thing is there are limits when you're above 50% power. The ramp rate limits is can be as low as 3% per hour. So you'd never be able to move power this quickly. A full power ascension takes days. And there's also additional feed water pumps you would place in service. There's a whole bunch of other things, but again, for a simplification, this is pretty good. Look at me losing points right now. But overall, I really like this. I'll put this game in the description. It's just a simple little interactive thing to teach about nuclear power. It explains things at such a high level, which I really like, and helps demystify a lot of things with nuclear power. So thank you very much for the recommendation, and thank you very much for watching. I'll see you next time.